Okay, welcome everyone to this continuation of the theory of lies. We're still lying a lot. I'm lying every day. I'm lying all the time. It's very sad. Hopefully I'm telling the truth right now, because we are, well, I don't know, hopefully. But anyway, we'll see. We are talking about the Baker-Campbell-Hausdorff formula, which is something you should have seen at least once in your life, and then you will never use it again. I don't remember a single time when I used that formula, ever. I don't even remember how the formula looks like. I only know what it does. And that's essentially what we're going to discuss. So will I even pull up the formula? Maybe. I don't remember anymore. We'll see. But it's an interesting thing. Okay, so here's again my favorite picture of, why commutativity matters. Hopefully at this point I've convinced you that commutativity matters. If you open the door and you walk through. Or you walk through the door and then you open the door, usually that is actually different. Community matters. Lie algebra we add, in the Lie group we multiply, logarithm exponential map. And the Baker-Campbell-Hausdorff formula literally compares those. What is lost along the way, how you need to do that, how the bracket enters the picture. Yeah, okay. So what we do is near the identity, we take e to the x and e to the y in the group and ask, well, take a logarithm of it. So Baker-Campbell-Hausdorff formula says that the logarithm of that thing, if they commute, it's just e to the x plus y, so it's just x plus y. But what happens if they don't commute? What is that? There should be some formula in x and y. And you could quit the video here. There is the formula for it. It's called the Baker-Campbell-Hausdorff formula. That's essentially it. As I said, I never really used this formula. It's obviously important because it compares how the logarithm and exponential map actually behave on Lie groups or non-commuting objects. But it's not nice enough to actually, we'll see. We keep on going. The easy case when everything commutes. So the bracket is 0. That's literally what it means. And nothing happens, right? E to the x plus y is just e to the x times e plus y. So the logarithm of that thing is just x plus y. As you would expect it from the inverse of the exponential function. Right? Inverse here, you mirror around the identity axis, and you have this nice inverse. Right? So when everything commutes, they're really nice friends of one another, or kind of anti-friends if you want. They undo one another, like antiparticles, I guess. Anti-friends. Let's say anti-friends. Yeah. So the formula that I haven't even showed you is very boring and easy in that case. It doesn't deserve a name. Maybe it would deserve a name, but it should be not of some mathematicians like Baker, Campbell, and Hausdorff, which were last century's mathematicians, but maybe more like from the 16th century or something. My historical knowledge here ends very, very quickly. But anyway, so this doesn't deserve a name, right? It's just boring. Just what the logarithm does anyway. And then comes the formula, and it's not that great. It has infinitely many terms in general. It's not that great. But maybe we just can remember the first part. So we have what we expect, and then a correction term, which involves the bracket. Excellent. So if the bracket vanishes here, everything vanishes, and we're happy. But non-commutativity means the bracket doesn't vanish, right? Remember, the bracket usually is just the commutator. Right, and if the commutator doesn't vanish, it's really just bracket xy is xy minus yx. So literally, if it commutes, it's 0, right? And if it doesn't commute, it's not 0. So if the bracket doesn't vanish, you have something non-trivial. Oh, I actually showed you, it's not really the formula, but this is roughly how the formula looks like. Oh, let's discuss it at least for 1 second, just for its glorious, magnificent, disgusting presence, I guess. So you take first order brackets, you take second order brackets, you take third order brackets, you take fourth order brackets, you take fifth order brackets. Fine. So let's not look at it anymore, and let's just keep on going. Let's just focus on the first term. Yeah. So essentially, right, higher terms involve nested brackets, so fourth order brackets, fifth order brackets, blah 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 blah. So eventually, the Lie algebra itself, the whole Lie algebra with all of its structure, controls the whole expansion, which is again a good reason why Lie algebra is not just the linear space, but it's also the bracket operation. You could see that without the bracket, there would be literally nothing you can do. Yeah. So literally, the bracket somehow remembers the non-commutativity of the story. That's essentially the formula. And meaning over memorizing, really, do we really need to memorize the Baker-Campbell-House stuff? Nah, we don't need to. If you want to, you're free to. Some people like to memorize the first 5 million digits of pi. If you want to do that, go for it. But you don't have to. Not the point, right? The important thing is usually not the full series. Usually you just take some terms of it anyway. And what it means conceptual is a little bit more important. Right? It translates a product into a sum, and there will be some loss somewhere. There will be some correction terms somewhere. That's just what it is. Huh? This is literally a near the identity statement, right? Globally, the logarithm is just an absolutely disgusting map. The logarithm is already an absolutely disgusting map in real numbers. Here's a complex logarithm, which is an absolutely disgusting map, which has multiple branches, and you have this Riemann surface type story. Oh my goodness, we don't want to do that. So locally, yeah, great. And globally, yeah, no, essentially. But that's the relationship between Lie groups and the algebras anyway. It's really only good locally. This is fine, yeah. And this is local. And globally, yeah, we don't want to think about it. Let's not do it. Oh, let me not do it. Why do we care? Well, essentially, it is the way to go between one and the other, right? Because if the Lie group is a logarithm of the Lie group, the Lie algebra, oh god, oh my goodness. The Lie algebra is the logarithm of the Lie group. And the Lie group is the exponential of the Lie algebra. We kind of want to know how exponential and logarithm really behave with one another. So it's a really important tool kind of for the structure theory of Lie groups, of course. Yeah, so this is essentially explaining why Lie algebra maps are the correct things of local Lie group maps and whatever, right? Locally, everything is kind of really nice. That's why we want to do it. Yeah, and yeah, so next time I will talk about differential structures and how actually homomorphisms can be differentiated to get Lie algebra maps. But the formula itself, which you don't need to remember, as I said, which I haven't even written down. So there's a closed formula to write down all the funny coefficients, for example, and all the funny terms that appear. Yeah, let's not do it. Anyway, the formula itself just explains that our Lie group and our Lie algebra are almost the same object, but non-commutativity makes just life a bit more difficult, as it usually is. That's why life is so. If life would be commutative, oh my goodness, that would be good. Or bad. I actually can't tell. But it would be probably easier. But life is not commutative, and Lie groups are also not commutative. Anyway, I hope you enjoyed this video, and I also hope to see you next time. And I realized now, next time, apparently, I'm trying to do that, and not that. Oh, we'll see what will happen next time. Okay, I still hope you enjoyed this video, and I hope to see you next time.